is basically do up to 3-inch. I have some samples here I'll show afterwards. And we can save a factor of 100 in the time of welding, as I'll show and explain. So first of all, in these sectors, we're reducing the production time. We are reducing the power consumption. Again, sometimes by a factor of 10. We use 10% of the energy that is being used with different other technologies. And we can use materials that are not in use today, so more recyclable materials. And overall, we're improving the return on investment for the customer. So when they buy our lasers, they can have much more efficient production and basically benefit financially and cover the cost of the laser within a year or so. So just a few words about Sivan. Like I said, we're the first and only company in the world that has this technology of current beam combining. We're what's called vertically integrated company. All the core technologies are done in-house. We manufacture the laser from the small components to the sub-modules all the way to the full laser, everything in-house. We have more than 90 patents on this technology. We're 165 employees in Jerusalem, Israel. And like I said, our focus now is in shipyards and tier 1 or OEMs for the car industry. And many research institutes that, like yourself, that get the laser to do the research. We started 2008. 2018 was the first time we sold what is now our main product, the OPA6. And in 2021, we sold the first 100 kilowatt laser. It's the largest laser in the world with single mode output for material processing. So these products today are in serial production, commercially available, and installed in customer sites. Okay, so what is dynamic beam laser? So when you do regular welding, basically you have the base material that you want to heat up, okay, until it melts. And then when it resolidifies, the two parts join, right? But when you do it with a torch or other heat source, the heat goes to all directions. So if you want to go deep, when you try to go penetrate the material, the heat also goes to the sides. Laser, because the energy is so focused, within a few tens or hundreds of microns, you can get kilowatts or tens of kilowatts. The heat just doesn't have time to spread to the sides because of the heat conductance of the material. It just happens so fast that you get to the melting point and even to the boiling point, and you get evaporation of the material. So what happens is that in the point where the laser penetrates the material, it melts the material, evaporates it, and because it evaporates it, it can penetrate even deeper. Okay, so you create what's called the keyhole. The keyhole is really where you have some gas inside the molten material. So you have the melt pool with the molten material, and inside the melt pool, you have the keyhole where you have gas, and the laser can penetrate through the gas and get really deep into the material and have deep welding without having a very large heat affected zone. The heat doesn't spread to the side so much. And it is all happening very, very quickly. So this is a simulation. Many of the simulations you'll see here are done by the Technical University of Vienna. It's a very, very detailed simulation. This 100 milliseconds simulation takes about 2 weeks to calculate because it takes all the physics that are happening here into account. It's a very, very precise simulation. So what you see is that we can weld here, and in a few milliseconds, the metal goes from solid to liquid to gas, and then cools off to liquid and to solid again. All this in milliseconds. So for example, we can go 30 meters per minute and weld something. Okay, that's 500 millimeters per second. And that sounds great. The problem is that the same things that are the advantage of the laser are also the disadvantage. It is happening so fast that it's completely uncontrollable. Because think that if in 1 millisecond or a few tens of milliseconds, the material goes from solid to liquid to gas and back, you can control the process. And the whole thing is propagating at 100 or 500 millimeters per second. And you have this keyhole, which is basically gas with high pressure, but around it, you have liquid metal. And the liquid metal always want to fall into this keyhole. So you have what's called keyhole instability. And really what happens in reality is, like you see here, that sometimes material falls and collapses the keyhole, and then you have porosity. You see the bubbles that are captured inside the material. You have sputter because things just fly out. And probably the worst thing is that you don't control the phase of the metal that it resolidifies to, right? So when the metal resolidifies, you can have different phases of the metal, and you can create cracks, you can create brittle phase of the metal. Sometimes it can become too hard. You know what I'm talking about, right? The phase of the metal is what are the properties of the metal, and this is determined many times by the cooling rate. You know, like if you take metal, you heat it up. If you let it cool slowly, it has one property. If you cool it fast, it becomes very rigid. So the point is that you do here a very dramatic process to the metal, and you don't control what's happening in the process. And that, again, is why, with all the advantages of laser, people don't really use laser for welding, especially not for things that have to be qualified, okay? Like in cars, in pipes, and everything that has to be a good certified weld. It's very difficult to do with a laser. But our laser, with the ability to manipulate the beam and create any shape of the energy inside the melt pool, we can really manipulate the beam at speeds of gigahertz or tens of megahertz, creating complete shapes. And all this to do at very high power, very, very fast, at any arbitrary shape, and very, very reliable. This allows us to control all the process. So all of a sudden, 1 millisecond looks like a huge amount of time, because in 1 millisecond, we have tens of thousands of time slots that we can engineer what's happening inside the melt pool. And what we control is two categories of things. One is the thermal distribution inside the melt pool. So we control the thermal distribution, thermal gradients, both in space and in time. Because it's dynamic and it's connected to the feed rate of the material, we also control the time aspect of it. So thermal distribution in space and time, and because we have the melt pool, and inside the melt pool we have the keyhole, and the keyhole is gas with high pressure. It creates forces on the molten material and pushes the molten material. And we can move the keyhole, create a few keyholes, move the keyhole from place to place and so on, so we can actually create flow of molten material inside the melt pool. Okay, so just to give you orders of magnitude, you're talking about something that's, the whole melt pool is maybe 1 millimeter, and the whole thing is happening in a few milliseconds. And I'm talking about inside, it is 1 millimeter, and a few milliseconds, we can do thousands of iterations to control the process, okay? And this is a, I don't know how familiar you are with these type of processes, but nobody in the world has anything that's even close to this. This is completely revolutionary, and it allows us to, first of all, stabilize the process, tailor the geometry of the weld, and control the resolidification process, thereby avoiding cracks, porosity, sputter, humping, and controlling the phase of the metal to what it resolidifies to. Okay, so this is really differentiating from anything that exists today, and that's why we can do today welds that nobody else can do, and therefore take, instead of traditional welding or brazing or electron beam welding, we can do it with a laser with all the advantages. So how does it work? How do we do it? So I only have one slide on the laser technology, just not to get too much off the topic of welding, but people always want to know, so how does it work? So the way it works is we have here many lasers. Our basic product has 32 lasers, and in the bigger ones we use 100 lasers. And from every laser, you have optical fiber going to some collimating lens. And the laser from the light from each of these lasers goes out through some optics and create a spot. And this spot is a few hundred micron. Let's say in our case, 300 micron spot, okay? So when you have 32 lasers, each one with 1 kilowatt, and they all, as you can see here, are parallel to one another, each one of them creates a spot of 300 micron with a kilowatt of power. And altogether, they create 32 kilowatts, but with a spot size of 300 microns. But because light is waves, when you have multiple sources that are coherent to one another, meaning they're all the same wavelength and they're all correlated to one another, if you have two waves that come in the same phase, they add up the energy. And if they come with opposite phases, they cancel one another. So what happens is that in some areas in the center, because of symmetry, they all come and add to one another. And in other places, they come out with different phases and basically cancel one another. So all this energy, in this example, 32 kilowatts, that was spread over 300 micron, all of a sudden is all condensed. All the 32 kilowatts is condensed to a very small spot in the center. In our case, it's about 50 microns, okay? So instead of having a spot of 300 microns, we have a spot of 50 microns with all the energy. Okay, so this is the beginning when it's not coherent, but when it is coherent, it all condenses to a small spot. And because the different phases, we can actually manipulate this constructive interference to happen where we want. So we have this constructive interference in the center, and by controlling the relative phases, we can manipulate the beam and make it move. And what makes the beam move is just controlling the phases, and controlling the phases is pure electronics. Okay, so we have a software and we have electronics, and we can change it at, like I said, at gigahertz, and the beam moves to wherever we want. Okay, this is the core technology. It's actually, if you took your basic physics, maybe even in high school or definitely in the first degree, this is just like a diffraction grating. There's nothing new about it. It's just extremely hard to do. It's like an interferometer with tens of sources at very high power. So it's very easy to explain, just very, very difficult to do. And like I said, nobody else was able to do it until we did it now. Okay. So in reality, that's what it looks like. You see the laser and the fiber going to the optical head. And from the optical head, you have tens of beams coming, overlapping, and on the workpiece, they're all focused to one point, and instead of being a few hundred microns, they're just a few tens of microns, and can move from place to place, both X, Y, and Z. You can also move it up and down, because basically with the phases, we create a virtual lens, so we can have full control on the position of the beam. So this is the core technology, this is the core capability, and now I'll explain why it's important. So before I do that, just two slides about practicality. When we want to design a beam shape, we provide a very, very simple software. Basically, it's a grid that you go with the mouse and go click, and wherever you click, you get energy. And if you click twice, you get double the energy. You click 3 times, you get 3 times the energy. So really, any energy distribution you want, you just go in this tool with the mouse and click, 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 and you create whatever energy distribution you want. And then you can also tell the laser how to go from point to point, because it's completely arbitrary. You don't have to go in some continuous motion. You can jump from this point to this point to that point, or you can have a few points at the same time. completely arbitrary control on how to distribute this 32 kilowatts of the laser inside the melt pool. Very easy to use. Takes 1 or 2 minutes to design any beam shape that you want. And then another important thing is that, let's say we design a beam shape. Now the orientation of the beam shape is also important. For example, in this case, if we have a beam shape that is 2 points, okay? Now, why would you do 2 points, for example? If you have a single point or any type of normal distribution of energy, the temperature is going to be like some kind of a Gaussian, right? Because you have heat source in the center, but the temperature spreads continuously. But if you have 2 points of energy, from each point you have some distribution, so the temperature distribution of 2 points of laser would be more like a top head, right? So this is just an example, but the point is, especially by the way, in 3D printing, if you go on the powder and you want to create some fine structure, you really have to control the temperature distribution. But also in welding, temperature distribution is really the key, and this is just what creates the temperature distribution. But the orientation of the beam shape relative to the propagation direction is critical. In this case, we have to be the 2 points that are perpendicular to the propagation direction. So if you would have some optics that creates instead of 1 point, 2 points, it's not enough, because as you go along on your workpiece, the orientation has to change. And it has to happen very, very fast. If you print, let's say, 2 meters per second, you have to change the orientation at a huge speed. You cannot do it with mechanics. But of course, electro-optically, you can change the orientation whatever way you want and very, very fast. And what you see on the left is actual fast camera where you can see 2 points, and as they go around, the orientation changes. Another point to say here is that the software, the interface, so on the left, it's done with a Galvo scanner, okay, just like everybody's using. And the interface, the software interface between the Galvo scanner or a robot or a CNC machine to our laser is very, very simple. We have a very simple protocol, standard protocol that people use today, and they can control our laser and give the commands of what's the power of the laser, what's the beam shape, and what's the orientation of the shape. Okay, so what do we do with it? So here's an example. On the right, what you see is simulations. This is from IFSW in Stuttgart. And what you see here, the color code here is speed of molten material inside the melt pool. And you see that you can design different beam shapes to create different currents of the liquid metal inside the melt pool at different speeds and different geometries. And on the left, you see the fast camera where we switch between 2 shapes. On the top, you see the shape with 4 points, and in the center, you see a shape of 1 point. And you see in the camera, you see the 4 points, and once in a while, we create a point in the center that creates these waves, okay? So this is just to illustrate that we actually create waves, motion of liquid material, liquid metal inside the melt pool, okay? And this is very important for many processes. I'll show a few of them. This is another example. What you see on the left over here is a top view of 2 pieces of metal. From here to here is one, and from here to here is another, and there's a gap in between. In this particular case, this is a pipe with a 3 millimeter thickness, and the pipe, when you try to weld the top seam, there's always a gap of a few hundred micron. So you can have filler material, but what we did here is designed a beam shape that acts like a shovel, and it takes material from the side and moves it to the center and fills the gap. Okay, this is really cool, and it works. So we actually are welding pipes like this where material comes from the side and being pushed to the center to fill the gap. Another example here, this is again from IFSW in Stuttgart, is welding of aluminum 7000. Aluminum 7000 is very sensitive to cracking. When it resolidifies, it cracks. That's why people don't use laser welding for aluminum 7000. But by creating these currents in the material, they were able to develop a process to avoid the cracks. The reason it happens, by the way, is because when you have the currents, you create a pressure gradient inside the melt pool, and the pressure gradients controls the motion of the molten material between the grains as they resolidify. Because in the resolidification, you have grains that resolidify, and if there's voids between them, you get cracks over there. But creating these pressure gradients inside the melt pool during the resolidification makes sure that these cracks don't happen. There's a talk, I have a link at the end to the talk of the head of the IFSW. It's fascinating, you should listen to it. It's just incredible science, how they developed this. Another feature that we have, we call it frequency. When we say frequency, we mean that, let's say if you have a spiral, you decided for some reason that the spiral is a good shape that you want to create, you can make the spiral fast or slow, okay? Frequency is how many times a second you finish a whole spiral. So if you say 1 hertz, it means it takes a second to create a spiral. If you say 100 kilohertz, it means you do it 100,000 times in 1 second. And of course, it's important, firstly, because of the dynamics inside the melt pool that are completely different if you move the keyhole slowly or fast. But also, when you correlate it with the feed rate, it means, are you going to repeat your motion inside the melt pool a few times or a few thousand times, right? So it's completely controllable. And again, just by the click of the button, you can do whatever you want. So here's another simulation that shows why it's important. So this is a shape that's very popular in the industry today of having a ring with some energy in the center. But people are using this statically. They have some optics or in the fiber, they create a ring and some energy in the center. By us, it's dynamic. The beam moves around. And you can see that if you move it at 2.6 kilohertz or at 260 kilohertz, you get a completely different behavior, both of the keyhole, the stability of the keyhole, the sputter formation, and the length of the melt pool. And here's a real example from with a fast camera. And the point here is that we have 2 different shapes. And what you can see that in the top, the material stays liquid this whole time, whereas at the bottom, it resolidifies very quickly. So that means that by providing kinetic energy to the material and by providing particular currents, you can control the rate of resolidification. And the rate of resolidification is what's going to control the quality and the phase of the metal when it becomes solid again, okay? So this is, again, a powerful tool that there's no other way to do, but now you can really control what's happening in this process of resolidification. Another interesting example is when you weld die-cast aluminum. When you do mass production, die casting is the most popular and cheapest way to do a complex part in mass production. The problem is that when you pour the aluminum at high pressure into the mold, it absorbs a lot of gas. And that's okay, it doesn't affect the properties of the metal, but when you try to weld it, all the absorbed gas boils, pops out, and creates sputter and porosity. So people in practice don't really weld die-cast material, they use other joining technologies. But with our laser, you can actually weld die-cast material because of controlling what's happening in the melt pool. And what's important to note here, the point of this slide is to show the difference between 260 kilohertz and 500 kilohertz. Because when we come and introduce to people, they say, the molten material, metal, these are big things. They don't move so fast. I can do it with a galvo scanner You know, IPG gives galvo scanners, and you can do it at a few kilohertz. Nothing moves faster than a few kilohertz, but it's wrong. Because when you're talking about these scales of tens of microns, and you have temperature gradients going from 2,700 degrees to 20 degrees, these huge temperature gradients and these small scales actually work in nanoseconds. And you can see clear difference if you're working at 250 kilohertz and 500 kilohertz. In fact, we have a lot of research that we do that even more than a megahertz, the keyhole and the melt pool feels the difference of these very, very high speeds, which is completely not intuitive, because if you think about heat, you think about, you know, it takes milliseconds at least for heat to go from place to place, but it's not true when talking about these small scales. Another really interesting example, again, going from, on the left, it's 100 kilohertz. I'm sorry, yeah, 100 kilohertz, 200 kilohertz, and 300 kilohertz. And this is welding of aluminum to copper. Now, welding aluminum to copper is difficult at any day because they have such different properties. And it's not only in the melting, but afterwards also in the resolidification. You get cracks and all kinds of things like that. But a very important thing in electrical contacts. In the EV, when you have the batteries and you have the bus bar, there are many times you want to connect copper to aluminum, but the electrical contact, the electrical conductivity, and the thermal conductivity have to be very good. But if you have intermetallic mixing, if the copper and aluminum mix with one another, two bad things happen. First of all, the thermal and electrical conductivity is poor. And second, it's a very brittle phase of the metal. And then when you put it in the car and the car shakes for 200,000 kilometers that it goes, eventually it's going to break. So having welding copper to aluminum without intermetallic mixing is critical. And you can see that by changing the frequency, we are able to get here a perfect weld, okay, with hardly any intermetallic mixing. Whereas if you change some parameters, you get a lot of mixing. Okay, so again, the point is it's very difficult to do, but you have the tools to control it and really get a perfect weld. And the idea is that the speed here is important. You cannot do it with just a galvo scanner. Okay, and then is what we call the shape sequence. A shape sequence means that we can pre-design different shapes. Okay, so we can design all these shapes, have them in the computer, and then we can tell the laser to go between shapes. So let's say you have the first shape for 1 millisecond, the other shape for 10 microseconds, and third shape for 10 milliseconds, whatever you want for different reasons. And I'll show a few examples why it's important. Okay, but again, full flexibility of anything you want to do. And the last feature is the focus steering, because again, maybe you know, anybody who worked with a laser, high power lasers, knows that you have to work very, very close to the workpiece, and your depth of focus is very limited, because even, let's say if you work 20 centimeters away and you want to focus all this energy to 0.5 millimeter, you use a focusing lens. But the depth of focus is very small, meaning that if you are a few millimeters away from the focus, already the spot is very big. Okay, so you go out of focus very quickly. Our laser is single mode, meaning that the dispersion, not dispersion, but the opening angle is very, very small. So you have an inherent large depth of focus. You can have tens of millimeters inherent depth of focus. But in addition, like I mentioned, just like we can control the motion of the beam in X, Y, we can also control it in Z. And we can actually control the position of the focal depth, and altogether the inherent depth of focus plus the ability to move it, you can have tens, and in the maximum we even reached 150 millimeters, 15 centimeter depth of focus. Okay, this is unheard of in any high power laser. And this is an example of cutting. So you see here a cross section of cut. where on the top it was fixed focus, and on the bottom it was focus steering, and you see much smoother all the way down. This is 15 millimeters, and no drus at the bottom because you have the hot spot all the way at the bottom. And of course, in welding is the same thing, just difficult to show this in welding, but also in welding, if you want to control everything that's happening in the depth of the weld, you can do the focus steering. Okay. You know, I always like, I don't know if to say it or not, but I'll say it anyway. If you don't have a lot of experience in laser welding, it's hard to appreciate this. But I'm telling you, there's nothing like it in the world. It's like really, really amazing, if I may say so. No, just to give you the context, because if you hear about this the first time, you say, oh, okay, you know, that's the way it works. It's not. This is unique. There's nothing like this anywhere else. So now I'll show you a few case studies. So first of all, in deep penetration, this is an example of welding of ship panels. If you do it in the traditional way, let's say if you have here an inch of weld that you have to do. First of all, when you do it with a torch, you have to put a huge amount of energy, and there's a very big heat affected zone. The energy goes to the side as well. You have to prepare a bevel here. And the most important disadvantage is that you have to go tens and sometimes hundreds of times with a filler wire. In order to avoid huge heat affected zone, you don't weld everything at once, but every time you weld just 1 millimeter, maximum 2 millimeters at a time with a filler wire. So if you have 25 millimeters and you have the bevel, you have to go about 40 times back and forth, each time filling up with a filler wire. With a laser, you just go one time and you're done. So, for example, this is an example that we worked out with a customer who ended up buying a laser. This is a 7-meter length of a weld. For this is a 25 millimeter thick material. They do a root weld with hybrid laser. Hybrid laser is a laser with plasma. So they can do the first 10 or 12 millimeters, and then the rest, they had to go back and forth with a filler wire, altogether 7 times to go back and forth. It takes them today 250 minutes, and we're doing it in 3 minutes. Okay, almost 100 times faster. And of course, the heat affected zone is much smaller, and perfect properties of the weld. So it's a huge saving in time, and huge saving in energy, and huge saving afterwards in fixing the distortion, because when you put so much heat into the part, you also have distortion that afterwards you have to fix. And here, all this is gone. You just go and it's done. So these are some examples that we did. So this first few, this is 25 millimeters, 40 millimeter, 50 millimeters. Up to here, we did it with these we can do with a 16 kilowatt laser. This we do with a 32 kilowatt laser. And this we did with a 100 kilowatt laser. This is already 3-inch. I have the sample here. Afterwards, I'll show you. So this is really very, very special. The other example is in battery coolers. So battery coolers are these plates that you put underneath the battery. Basically, they're the size of the whole bottom of the car. The ones we're doing now are 1.6 meters by 2.2 meters. And the batteries are sitting on them, and this does the thermal management of the battery. It's made from 2 very thin sheets of aluminum. Okay, each one is about 1 millimeter. In the top one, you make these shapes of the water pipes, and the bottom one is flat, and you connect them to one another, and that's how you create the whole manifold. So it has to be hermetically sealed and withstand high power, also all the shaking of the car. Today, it's being manufactured in brazing. So the brazing oven, the brazing furnace for this type of plates is 80 meters long. It uses 4 megawatt of energy. Some of it is electric, some of it is gas. So it's huge and expensive. And we can do it with 10% of the energy. So it's 90% saving on the energy. And a small room, basically a quarter of this room, is enough to manufacture this type of thing. And of course, the cost of each one is lower. So it's a huge saving on the cost per part, millions of dollars in saving over a few years of operation. And of course, the carbon footprint, you save 90% of the energy. So it's a huge saving also in the terms of carbon footprint. These are a few examples. We can do it at different types of aluminum, by the way. Today, people do it in aluminum 3000, but we can do it. If you do it in aluminum 5000, it's much more, it's stronger. Aluminum 5000 or 6000, it's stronger, so you can use thinner aluminum and get the structural strength. But it's just very difficult to do because it's crack sensitive, but we are doing it. You can see here 500 millimeters per second. This is 30 meters per minute. And this is also aluminum 3000 and different configurations. And also, this is very interesting, aluminum 3000 to aluminum 6000. Again, for different consideration, our customers always request different things in order to, they always try to minimize the amount of aluminum. So if you can use some of it for the cooler and some of it already for the structural strength and some of it to enclose the battery cases inside and to combine as many functions as possible, you save a lot of aluminum, a lot of weight, and a lot of workmanship. But in order to do it, you have to be able to weld these type of materials. So we're showing this capability to do that. The other example is die-cast material, as I mentioned in one of the examples before. But when you do die-cast material, all the gas that's absorbed boils and creates sputter and porosity. But we can manipulate the beam and go a few thousand times inside the melt pool as it goes in a very high feed rate and basically get all the gas out without having blowouts. So we demonstrated several of these products. And again, the way they do it today, at least these customers are doing it with friction stir welding. Friction stir welding, the speed that they're doing today for this product is 0.2 meters per minute. We're doing it at 9 meters per minute. So it's 45 times faster, okay? Not 20% faster. It's a factor of 45. That's the difference between the technologies. This is some cross-sections of some parts. Another example from automotive is the hairpins. The hairpins for the electrical motor. So you have these two copper pins that you want to weld to one another. The problem is that they are not perfectly aligned. There's always a gap between them. Sometimes there's height difference. Sometimes their shape is not perfect. And if you just come with a laser from the top, some of the energy penetrate through the hole between them, okay, and damages the isolating layer between them. So first of all, you waste a lot of energy, but second, you do damage with the laser inside. We have a beam shape. This is a sequence of two beam shapes. We have for 5 milliseconds, we have a beam shape of these 4 points that just hits. This is the top view of the hairpins. So it just hits the hairpins over here. In 5 milliseconds, it melts it. So they collapse into one another. And then we have this beam shape for another 5 milliseconds just to stabilize the whole melt pool and re-solidifies to this bubble, okay? So everybody's working on doing things like that, but you have to do it without damaging the bottom. You have to do it when you have high tolerances between the different pins. You have to do it fast, and it has to have zero sputter and zero porosity. The sputter is because if you have sputter, it's going to make shorts in other places in the engine. If you have porosity, over time, this porosity with the shaking of the car, it is going to open up to cracks and break. Another very big advantage of our laser in production of the electrical motors is because we are single mode at high power, we can work a few meters away. today, what you see here, you have the rotor, and you have a galvo scanner that makes the laser go from hairpin, couple of hairpins to a different couple of hairpins from place to place. But the field of view of the galvo scanner is not big enough to cover the whole rotor. So the whole rotor has to turn around. So you do a few hairpins, it turns, you do more, and so on. Because we're single mode, we can work from far away, and then the field of view of the same galvo scanner covers 3 or 4 times the area, so you can do the whole rotor without moving, mechanically moving the rotor. So again, it's a huge time saver, and just the infrastructure, just the whole mechanism of how to do it is much simpler. Okay, I'm almost finished. Aluminum 6000, I mentioned, is very difficult to weld because it's crack sensitive. So we have 2 customers, IFSW, that I mentioned a few times, at the research center in Stuttgart, and BBW, they're actually a manufacturer in Munich. They both have FR lasers. They both wanted to develop processes for aluminum 6000. They both developed their processes, and they're nice enough to share it. But it's interesting that they developed 2 different approaches, but it's nice to see it. So this is BBW, where they designed this beam shape that creates some motion in the melt pool, and you get a perfect weld compared to a standard laser of IPG or TRUMPF, that the most beam shape that you can do is make some kind of a ring with some energy in the middle. This is the best shape that they can reach, but still you have here a lot of porosity, and usually you have cracks, and here you see there's no cracks. So with our beam shape, they're able to do no porosity and no cracks. IFSW designed something else. They designed these 2 beam shapes here on the left, and they switch between them. And when you switch between them, you can see here they switch at 1000 hertz, meaning switching between the shapes. Each shape by itself is dynamic and moving at much higher rate, but switching between the 2 shapes, if you do it at a kilohertz or 100 hertz or 10 hertz, you can see in the simulation how you have completely different flow inside the melt pool, and you get completely different results from each type of these welds. And this is the real high-speed camera. You can see here how it switches. You see the triangle pointing to the forward and then backwards. Also here, it's pointing backwards, now it's pointing forward. This is 10 times slower than this, and the other one is much slower, and you get completely different behavior of the weld. And this is the last example. When you have sheet metal, it always comes coated to protect it from corrosion. So it's zinc coated or aluminum coated. In this particular case, this is a customer that has zinc coated material. And when you try to weld, overlap weld of coated material, the zinc in the interface evaporates and creates voids, porosity, which afterwards turn into crack. So usually you have to do something about it, either take away the zinc or make some space between them to let the zinc go away. But we were able to show with controlling the weld process that we are able to weld these without having a space between them and without having the coating away. This is still in evaluation stage, but it looks very promising. Okay, let's skip this. Okay, so this was all about welding. Because you also do here additive manufacturing, I have just 3 slides about the additive manufacturing. But everything I said about controlling the melt pool and controlling the cooling rate and controlling the resolidification process is just as important in additive manufacturing, maybe even more. So everything I said on controlling the melt pool is an advantage in additive manufacturing as well. In addition, this ability to manipulate the beam can also help in speeding out the process by by complementing the mechanical motion of the galvo scanner. So a galvo scanner is made from two mirrors, right? One for the X, one for the Y. But if you want to make a square, so the X mirror has to slow down to a stop, and the Y mirror has to start from 0 to accelerate. And this takes time because it has inertia, it has to stop, and it has to start. But if you can have the galvo scanner just go on a continuous motion, okay, just make a circle, and electro-optically move the beam to make the fine shapes, you can make everything work very, very fast, okay, and very accurate. And that's what we're doing. So first of all, in terms of controlling the melt pool, you can increase the speed because you control what's happening there. Today, if you put too much power into the powder bed, the grains just fly away. You create thermal currents over there and all kinds of sputter, and you just cannot put. It's easy to get a kilowatt laser or a single mode, but if you put kilowatt laser on the powder bed, the grains are just going to fly. By controlling what's happening there, we can make it much faster, higher quality, difficult geometries, and different materials. And in terms of the supplement in the galvo scanner, I'll just show the bottom line that you can go with the galvo scanner, go slowly, and I mean go fast, but inaccurately with the galvo scanner, and electro-optically jump to many points simultaneously, like in 1 millisecond. Instead of sintering 1 point, you can sinter 10 points. And you can go very inaccurately and fast with the galvo scanner and still be very accurate electro-optically. That's it. We are based in Jerusalem. We also have an office in Japan, an office in Germany, and hopefully soon we're going to have an office in Detroit. Thank you.
We can just open the floor for questions if there's any questions. And for those online, it may be easiest if you enter them by typing it into the. For those of you that are online, please type them in the chat and then we'll read them off so that everyone can hear them. So if there's any questions.
Some maximum gap that you should have
Okay, so we can probably go up to 1 millimeter or so, but it really depends on many parameters.
Yeah.
There are two elements to the gap. One is what the laser will do. And with the laser, we can actually go to a longer focal distance and then be able to cover a larger area. But also in terms of the weld, if you have too much of a gap, at the end of the day, you're going to have underfill, just going to miss material, even if you bring from the side. But we can overcome a lot of it. Yeah, so.
That's what we're doing. We have gotten the think about it, right? Sometimes you can get what's the sugar rates, sugar going through. That happens basically with the laser. We're trying to close that gap.
So that's like a blowout from
Yeah.
the laser process.
Yeah.
Right, exactly. That's exactly what we are avoiding. This is exactly the process that happens many times. All these blowouts. That's the sputter that you get all over the place, and that really, let's say, in electrical motor, it actually creates shorts and ruins the motor. Yes, this is exactly what we are controlling to avoid these blowouts. Yes. Yes.
Just repeat the questions.
Well, and will the one that's instead of changing the direction or gather fire development?
I think that the question really relates to thermal control. So after you've done the melting, can you go back and control the cooling rate with part of that beam? Is the beam large enough to reach into the cooling zone to control that?
Yeah, absolutely. This is exactly part of the thing we do is controlling the cooling rate. And controlling the cooling rate, we can do in two ways. First of all, we can divide the energy. So we can have like a front end, so to speak, of the beam doing the process, and then a back part of the beam just doing the post heating just to get the cooling rate slower. But also what we found is that by adding kinetic energy, we can also control the cooling rate, because maybe, you know, the temperature might be the same, but it's only going to solidify at a lower temperature because it has energy. So really what you want to control is the cooling, is the solidification rate, and that is definitely a major part of what we do.
Right, and I have a question in the chat, and from Keanu, I believe it's wondering if it's possible to apply this technique for laser pulses as well. If so, how fast can the beam shape be altered, and how short can the laser pulse be? And then there's a few more here as well.
Okay, yeah, so it's a great question. Definitely the answer is yes. But first of all, we're not doing it right now because we have to focus. What we did do is demonstrate that we can do the same type of coherent beam combining and beam shaping with nanosecond pulses, because a nanosecond pulse, the way it's generated is basically you have a cedar, an amplifier, and you just modulate the cedar at nanoseconds. And then for us, it's completely transparent. Whatever we do in CW, if the cedar is modulated in nanosecond, it works. We demonstrated that. When people go to picosecond and femtosecond, it already becomes more complex. But if you do this in nanosecond, you can get 30 or 100 times the peak energy than if you do it just with a single laser, and you get the dynamic beam. So the answer is in principle yes. We're not doing it right now.
Right, and then the next question relates to part traceability, and I think it's more like a quality question. So the big push for scanning and validating laser weld after they're completed. Do you have a similar system to LDD? So I'm not sure if you're familiar with LDD. It's not a company I'm aware of, but so it really goes back to
maybe in terms of quality, I can
what techniques have you used to assess final weld quality?
Yeah, exactly. So our customers are going through certification processes for all the welds, but because most of the time we don't have access to that data, and even when we do, we're not allowed to publish it. We ourselves started going through qualification process. So we do X-ray, CT, and then we measure the Charpy test and the strength test and the strain and the hardness test and everything according. There's a standard basically that you can certify a weld according to the standard, and we're going through this to show that the welds are certified.
Yeah, I think they did have a follow-up comment. So I think it's more the partners that you're working with, some of the experiences you've had with them, how they're assessing that inline weld quality. So as they're welding, you showed a lot of simulation.
Okay.
Are you aware of people who are doing that inline process monitoring with your laser technology?
Absolutely. So all the inline monitoring, like OCT, spatter, thermal cameras, regular fast speed cameras, everything is being done with our laser, just like they're doing with others. I can say that some customers do it, but really what you want to do is qualify a process until it's good enough that you can just trust it and then do just samples. Still, it really varies. Different customers do different things, but whatever monitoring people do in real time to the weld quality, they do also with our laser. It really depends on the customer.
Right. Very good. So I don't know if there's any other questions. Oh, yeah, go ahead, Rachel.
Thank you very much. I was wondering about like some of the temperature rating related in the sheet size, how like your examples had a lot of them for the quality, but how does that change based on the material being used, and how does the material affect sort of the heat penetration that would kind of achieve? Would that be dependent on the strength of the material as well?
Yes. So first of all, the temperature will always get, not always, but most of the time get to a keyhole, which means that it gets to the evaporation temperature. So it's going to be close to 3000 degrees, depending, each material is different, but you would get to that temperature to create the keyhole. And then the temperature distribution around the piece would depend a lot on your feed rate, size of beam, and so on. But in general, the faster you work, the smaller your heat affected zone would be. But you always, the peak temperature would be the evaporation temperature. And then if you have thicker material or thinner material or material with better thermal conductivity or worse thermal conductivity, you have to adjust the power to the process. So let's say if you weld mild steel of a few millimeters, you use, I don't know, 3 kilowatts. The same thing for aluminum is going to require 6 kilowatts, and the same thing for copper is going to require 9 kilowatts. So it definitely depends on the properties of the metal.
Yes.
Is any relation to the plasma reports?
The ionization rate in the plasma that's created in the keyhole. Okay, I don't have these numbers in my head, but we did look a lot into it, definitely in the simulation stage, to make sure that when you have deep penetration, the plasma doesn't stop the laser. So it's definitely an issue, and being able to keep the keyhole open and get rid of the plasma is critical. Otherwise, when you get to too high power and deep keyhole, the plasma basically blocks the laser. So I don't have the numbers, but it is an issue that we had to deal with here. It's I have to say the physics inside this process is amazing. It's like really interesting and complex. I assume it can. I mean, because you just use huge amount of very condensed energy. Yeah, we never looked into it, but I mean, for us, it's a problem we're trying to avoid, but it is there. So if you have enough intensity, you will create plasma.
All right, go ahead, Sebastian. This will be the last question. We'll kind of wrap things up.
Obviously, this is massive implications for large scale industry and automotive shipping and aerospace. Do you see this technology being used smaller scale as well, even in smaller shops, smaller production facilities?
Yeah.
And even replacing plastic manufacturing motors?
Yeah, good question. Good question. So I would say like this: if you have special processes that you have to do and you just can't do it in a different way, so the answer is yes. But I mean, our laser is expensive. It's an expensive equipment. So you have to calculate your return on investment, and we always do it with the customer. So if you have a process that you just can't do other way, so of course, or let's say if you're replacing electron beam, even if you have a small scale, even if you make just a few parts, but you have to go to an electron beam welding, our laser would be cheaper and easier and cheaper cost per part and so on. If you're building ships, so if you're a small shipyard, just don't have enough work, and you build one ship a year, and you're just looking for work, so you don't care if your workers work for the whole year or work only for 1 month, you're not going to buy our laser. But the big shipyards today have a huge backlog. By the way, the offshore structure and the windmills, the offshore windmills, they have a backlog of 3 years. They just don't have enough welding capacity. It just takes too long. So for them, it's a huge saving. But yeah, it really depends on the application.
Very good. So thank you very much. Let's thank the speaker one more time. So for those that are online and interested, I'll take my phone and I'll just walk around the lab and just show you our facility here. And then for the rest of us, thanks. We have lunch in the kitchen. So come and join us for lunch, and I'll be back momentarily. So I'm just going to just walk around.
Thank you very much.
Hi there, everyone. I'm Stephen Veltheis. I'm just going to walk around our lab and give you a